Okay, so again, if people want to access the script to run the kernel density estimation, that's again on that materials page here under KDE. So it's going to be using the same package, the AMT package, but now we'll be using kernel density estimation. Chat with me. Okay, thanks, Ashley. Okay. All right, so as long as you go to that site, you can get the code. So you'll just open that up in R. And you'll see that there's a couple other new R packages here. So we're using the tidyverse and Lubridae packages again, like we did previously, as well as the AMT, SF, R Natural Earth, Plotly packages. I'm using the TikTok package again to do some timing. At least in some cases, when I was originally trying to do the least squares cross validation method, that was taking a while, although it ended up taking too long and not working. So I won't be covering that here in this case. Now I'm using the Met Brewer package for different color palettes and the units package to be able to show spatial units when I'm making plots in ggplot. Okay, load all of these in. All right. Now I'm going to read in the data. So again, this is the same data set we've been working with as exported from the state space model. And same as before, we need to modify the date column to be in a date-time format. And because we're using the AMT package, we need to use this make track function to get it in a format that this package can use. Although in this case, instead of using the longitude, latitude, I'll be using the X and Y coordinates, which again are the world Mercator projection in kilometers. And since this is not the default set of units for this projection, we need to define this proj string in a custom manner where we're setting units here to kilometers. So that's what I'm doing here to define this dat track object. And then one thing we need to do for this package when creating this kernel density estimates is to make like a template raster for it to map onto. So whenever you come up with these kernel density estimates originally, it produces like a raster layer. And we want to define what's the spatial resolution of this raster layer. We're going to be essentially using the same coordinate projection system, but we want to decide or define what the resolution is. And this is dictated based on the units that we have here for this projection. So using the make trast function, so make template raster, based on the dat track data sets, we're setting our res or our resolution to 4, which since our units are kilometers, this is a 4 kilometer by 4 kilometer grid cell. So I'm going to call this object trast for template raster. Now we have this object, so it's just essentially an empty raster. If I print this in the console, resolution is 4 by 4. It tells me the dimensions, so number of rows, number of columns, total number of cells, and then the extent and its coordinate reference system, but there's no values. Okay, so now actually moving on to estimating space use with kernel density estimation, we need to use the HRKDE function from the AMT package. So before we use the HRMCP function, the KDE is used for kernel density estimation. And in this first example, I'm going to be using the reference bandwidth method, just again to show one example of how to calculate space use. But again, in general, I don't recommend using the reference bandwidth as kind of your final product when estimating space use. So we need to supply the AMT object here, the dat track objects, our template raster that we just created. Then we need to tell it what method we want to use to estimate the bandwidth. So in this case, we're using the HRKDE ref function to say that we want to use the reference bandwidth for this data set. And this is the default for this HRKDE function. So if you didn't specify this, this is what it would just do. But we're going to modify this a little bit later, this argument, when we're using the plugin method. And then same as for the minimum complex polygon, we're defining the levels. So the isoplets that we wanted to return, and these are our 50% and 95% contours, essentially. So if I run this line and then print the results, again, it returns part of our data sets, tells us the coordinate reference system, the levels that we wanted, our template raster system that was used, or raster layer. And then here, UD is our actual kernel density estimate raster layer. So we have, again, all these different values up at the top, but then now we have actual values for these estimates of spatial intensity, essentially. And you'll see just above that, this H element of this list is showing. So this is our smoothing bandwidth for the reference method. And we see that it's the same in both the X and the Y dimension. So that's why there's two values here. And again, this is showing that it's using the kernel density estimation to measure space use. Okay. And we can make a quick, simple plot with this, just using the plot function and choosing colors for the different contours. So again, this is for all individuals here. And depending on your question, you may want to estimate space use across all individuals grouped together, or you may want to estimate them separately. So when grouped together, it identifies these three main regions. So the blue is the 50% contour or isopleth, and this is the core area essentially being used by this population or subset of individuals. And this is primarily focused around the island of Fernando de Noronha, but this polygon is actually quite large. So there's a lot of this space that's not even used by these turtles. And then for the 95% isopleth or contour, we see that it's also encircling the islands as well as these two different foraging regions next to the mainland. But these are also quite large. So there's plenty of the space that's actually overlapping with land. But in general, a lot of times it's nicer to look at when you're creating these plots to produce contours to put on a map instead of a filled in polygon. So to get these contours or these isopleths, we're going to use the HR isopleths function from the AMT package on our objects that has our kernel density estimates. And I'm going to call this KDE href for the reference bandwidth and then contours. So that's what we're extracting. And then again, loading in the spatial vector layer for Brazil, and then creating a map using ggplots. So this is just showing how you can plot a raster surface of this spatial intensity. So this is showing something very similar to what we just had before, where instead of polygons, it's showing the continuous surface, where before it was making these cutoffs. But now you can see this kind of over a much smoother area, and then with respect to land here. And in some cases, you might want to show this continuous raster surface, but a lot of times it's just easier to show either contours or these like semi-transparent polygons, filled-in polygons. So we'll make another plot, but this will be just the contours themselves. And this allows you to see the tracks a bit better as well. So in red here is our 50% isopleth, and in blue is the 95% isopleth. And showing, again, these kind of utilization distributions for the entire region in blue, and then the core area, or what would normally be considered the core area by most studies, in red. And again, a lot of these contours, these 95% contours, are overlapping land, which obviously will not be used here by these sea turtles. So I think we can do much better in terms of how we estimate space use. But this is a start. Okay, so that is the reference bandwidth method. The plugin method is going to do, we're going to use this very similar process with some slight differences. So here initially, I'm going to be estimating the bandwidth value based on this plugin method using the HRKDE PI function here. And then I'm also setting this argument rescale equal to X bar, and that is to deal with some potential errors I was running into when initially calculating or fitting this on my own. And if we just print this, we see we have two values here, similar as we had before for the reference bandwidth, except these are different. So we see that the reference value in the X direction is much larger. It's a value of about 4.5 compared to the Y direction, which is about 0.2. So we're accounting for these differences in smoothing in each direction, the X and the Y direction. And then we use the HRKD function again, and everything stays the same except for H. We're supplying these bandwidth estimates we just calculated from this HPI object. And you may see errors like this where it says binning grid to course for current bandwidth, where it may ask you to increase the grid size, meaning increase the resolution. So it's a finer resolution than you currently have. And that may be needed, but that might be something you need to go through on your own and tweak a bit. But then you also want to come up kind of ahead of time what spatial resolution you want to use, and that will also be dictated by the spatial scale of these movements of the tagged animals you're evaluating. So again, if we plot this new object we just fitted, but we're using the plugin bandwidth estimator, we have these same different components in this outputs and a new raster layer here that's been created. And if we create a quick plot, we can see that these contours are much, much smaller compared to the reference bandwidth. So we have now 4 different 95% contours here, or 95% contours for these tag turtles. And we can't even see the 50% contour isopleth polygon. So it's kind of buried here under these points at Fernando de Noronha. So we would need to zoom in a bit to be able to see it well. But this is a stark contrast to the reference bandwidth estimator. And this appears to do a better job in terms of identifying the areas of greater spatial intensity, because obviously they're not spending much of any time in open water in this pelagic region. It's not until they reach the mainland that they start slowing down and spending more time in different areas. Now, if we extract the contours of these isopleths based on these results, now we can make some plots and ggplots. So things show up a bit more clearly, where it actually looks like we have a 5th smaller contour here that didn't show up well in the previous plot for this one individual that migrated north for this 95% contour or isopleth. And now we can see the 50% isopleth here at Fernando de Noronha. So again, by comparison, the space use for this 95% utilization distribution is many orders of magnitude smaller than that from the reference bandwidth estimator. So you can see how important the value of these bandwidth estimators are in terms of how it modifies these results. Okay, so if you were to calculate the kernel density estimate per ID now, not just for the entire population as a whole, we're going to go through these next set of steps for both the reference bandwidth and the plugin method. And one thing I'm using for this process, which isn't as important since I'm not doing the least squares cross-validation now, which ended up taking a long time, is something that Vic mentioned yesterday, is you might want to install a package that makes a noise when your code is done running. So similar as what you have for the TikTok package for timing your code, and when you have talk at the end, it stops the timer. In this case, if you have a chunk or a line of code after your code finishes running, it'll make a noise of some sort. And this one package that I recently discovered that's only available on GitHub will actually produce a small short clip of different rap songs, essentially. So this is my way of showing this to you. And if you're interested, you can download it from this link here or using this code to install it directly from GitHub. Okay, so we're going to start again with this reference bandwidth. And as I've done before, first I'm going to split this track up by individual into a list, and then use the map function from per to map this HR KDE function per individual. And then eventually bind all of these polygons together. So in this case, I'm expecting it to take about 30 seconds, and we're going to have a Rick Ross brief clip to run to let us know it's done. But this is particularly useful if things take much longer and you don't want to pay attention to watching your screen, but you do want to know when it's done. And I can't highlight this without scrolling off the edge of my screen. Come on. Okay. So again, this should take about 30 seconds or so. And in cases like, there we go. Okay, so that's Rick Ross. Obviously, it'd be nice to have a progress bar or something else to let us know how long it thinks it's going to take, but that's why we time the code and write comments to ourselves. Okay, so now we have those contours essentially, and we're going to add in a new column to give the ID label for each polygon. And then we're going to map it with ggplot. All right, so here's a facet plot where we have the reference bandwidth estimator estimating the 95% and 50% isoplets per turtle. And this is showing the full extent of all turtles for each map. So obviously you can't really see the resident individuals that well because it's just super small by comparison. But when looking at each of these other three migratory individuals, we can see that these polygons are still quite large. So obviously much larger than the area they are expected to be using. Okay, so that's the reference bandwidth. And for the plugin method, we're essentially going to do something similar. So one thing I do want to note here is that I'm actually going to be needing to run this slightly differently based on which type of movement patterns these turtles are exhibiting. So you'll see here on these lines from 148 to 150 that I'm creating a new column for each individual called pattern. And I'm identifying or denoting whether I think they're resident or migratory. And that's going to impact, essentially, I think the spatial resolution that I'm going to be estimating at to get this working properly. So if they actually migrate from the islands, then I'm labeling them as migratory. If they stay east of this longitude value, then I'm going to label them as residents. Okay, and then I'm creating index to signify or denotes which list elements I consider residents and which are migratory. So for the migratory individuals, I'm going to be running these where my spatial resolution is 1 kilometer. Here we have DJ Khaled. We the best. And then for the resident turtles, I'm using a resolution of 0.1. So it's an order of magnitude smaller, and that's because they're not really moving anywhere. So if we left it at the same spatial resolution, potentially all of those points may fall into a single pixel, single grid cell. So we can actually see some spatial patterns. I'm making this even smaller at 100 meters by comparison. Oh, didn't run that. So this next one is Lil Jon. Come on, computer. Yeah! So there's so many options you can choose from. It's great. Now, again, we're going to create an ID column and then plot all these together. Again, this is using the plugin bandwidth estimator. All right, so now they look, again, much smaller by comparison to the reference bandwidth. So for this first individual, we see these much smaller ellipses around the foraging region and the original breeding location. And in each of these spots, we also see a core area or at 50% isopleth. So we consider this bimodal. For the second individual, again, there's two main regions, although there are some spots, it appears, during that migratory path that it's denoting as part of that 95% isopleth. And for the two resident individuals, those don't seem to have changed much. But for this last migratory individual, we have these two main hotspots or core areas at these foraging grounds. But then there's even a period where it's hugging the coastline towards the end of the track that's moving relatively slow, and that's added to this 95% contour. So now to make some comparisons more explicitly between both of these methods, instead of just looking at these maps, I'm going to combine these data sets together. And now we can actually compare the areas estimated by each method for each isopleth level or contour level. So area in square kilometers is on the y-axis, and then the level of the contour or isopleth is on the x-axis. So in green is the plugin method, and blue is the reference bandwidth method. So we see that first thing that jumps out to me is that the plugin method in green is much smaller in both cases compared to the reference method, although the differences aren't as bad for the core area, the 50% isopleth. But you can see what these differences might result in if you were to use one bandwidth estimator versus another, and making these inferences of how much space these different individuals are using, especially when there's implication or management or conservation implications at stake. So this is definitely important to consider a good method for estimating space use. So in general, it appears that the plugin method would probably provide a better measure of space use by comparison to the reference bandwidth estimator here.